Hello everybody, welcome to our webinar. My name is Vladimir Podnos, and together with my colleague Alex, we will discuss today a very important topic, iron core loss calculation with QuickField. For those who are new to our product, I will briefly introduce it. QuickField is a multi-physical tool for simulation of a wide range of engineering applications. Analysis models cover electromagnetic analysis, heat transfer, and mechanical stress. These types of analysis can be performed individually or in cases when the physics is more complicated and require combined simulation. QuickField supports the coupling between different types of analysis performed on the same geometrical model. One more important feature of QuickField, especially in the context of our today's topic, iron losses, is possibility to extend the QuickField functionality by adding the external models, which may communicate with core QuickField functions using application programming interface, which is called ActiveField. And from variety of QuickField analysis models, our main focus today will be on the magnetic analysis model group. They include DC magnetics, AC magnetics, and transient magnetic analysis. Applications for QuickField magnetic analysis are very diverse, but in many of them, the physical principle of a device or technology operation is based on use of materials which have very different magnetic properties. And combination of the media with low magnetic conductivity, like air, and highly conductive media, like carbon steel, allows shaping the magnetic field the way engineers need. Similar to electric wires in electronics, magnetic cores deliver magnetic energy from the sources to critical areas and minimize stray fields outside these regions. For example, in electrical transformers, the iron core delivers the magnetic flux from primary coil to the secondary coil. In conventional electric motors, similar task is performed by the steel stator and rotor, which minimize the magnetic flux travel path in the air. And in induction heating, magnetic materials increase the heating effect. But these materials, which exhibit high magnetic conductivity, in the alternating or transient electromagnetic fields, manifest also energy losses. These losses are usually called iron or core losses, and they are attributed to several factors. First of all, alternating magnetic field causes the structural changes in the material on the micro level due to the magnetic domain polarization. These changes consume energy. They are related to the hysteresis effect and usually called hysteresis losses. Other source of the core losses in alternating fields are induced electric currents. These materials are usually good electric conductors. This means that in the alternating currents, in the alternating magnetic fields, which induce the electric fields, electric currents called eddy currents will take place. And we know that the currents generate the heat. To minimize these currents, special measures may be taken. For example, lamination, thin sheets electrically insulated from each other are used instead of solid bulk material. And electric conductivity will be greatly decreased without much changes of the effective magnetic conductivity. But even with very thin laminations, small eddy currents still exist, and in some applications this also should be taken into account. Physics of the magnetic core losses or alternating or transient magnetic fields is very complicated, and there are various models offered to describe these processes. For practical engineering, there are two popular approaches: frequency Steinmetz model and more contemporary Bertotti expression. Factors used in both approaches, frequency of the magnetic field alteration, symbol F in the slide, and magnetic flux density, B. Also, several numerical constants are used which should be obtained from experiments or provided by the magnetic material vendors. Steinmetz's formula does not divide the losses by their physical origins, while Bertotti approach explicitly separates eddy current, hysteresis, and excess losses. This is the most popular method today, and this slide shows possibility to define the Bertotti coefficient in QuickField blocks using our data editor. This topic is subject of extensive scientific research, and new methods and models are regularly offered. When we discussed with our customers possible approaches for loss calculations, we found that some of them are not satisfied with standard formulas and prefer own calculation methods. So there is no established consensus on how to calculate magnetic core losses in all the cases. And we decided to make two things: implement most popular method, Bertotti expression, in QuickField AC magnetic analysis models for our major audience, and provide experts with possibility of using their own formulas if they prefer so. So, for using own formulas in core loss calculations, special objects and methods are added to our application programming interface, ActiveField, which I mentioned before. This is the most advanced approach, showing allowing calculation of magnetic core losses in both AC magnetics for sinusoidal alternating fields only, and for arbitrary shaped pulses using the transient magnetic analysis. This will be the major part of my colleague Alex's presentation. And we will demonstrate today what, as with any other QuickField feature, implementation of the magnetic loss calculation in QuickField can be performed simple and straightforward, because QuickField is a unique tool which doesn't require training. Now let us see live demonstration of QuickField models and calculation of losses in various scenarios. Alex, please continue.
In our practical part, we will follow all the steps required to build the model in QuickField and get the losses value and calculate the temperature rise. In practical part of our webinar, we will follow all the steps required to build the model in QuickField and get the losses value. First, we will take a look at the experimental data and we'll get the iron loss coefficients. Then we will run the simulation of the transformer in the no-load state and calculate the iron losses in the core. And the last we will take a look at the transient problems.